grayscale, which is slightly lower contrast. So which of these looks like it has a higher contrast? Yeah, so the one on the left. So if you look here, it's either black or it's white, more or less. Whereas here you've got a whole lot of different shades of grey. So that's a lower contrast on the right, and a higher contrast on the left. Radiographic versus real density. Again, it's going to be in the final exam. Again, half of you are going to fuck it up. Highest radiographic density is air. Highest radiographic density is air. It's black. High density. X-ray generators. They have single phase. So single phase, and then you can have half rectified, where the other half gets flipped up and then fully rectified and all that. You can get three phase, which they have basically three sine waves going through, and then you can have high frequency. So the benefits of a high frequency voltage supply, you basically get a continuous continuous stream of high speed electrons, which leads to even bombardment of the anode, so it doesn't fail as quickly, so you don't have to replace the tube as much. You get more efficient X-ray production and decreased X-ray exposure times. Less motion artifact for that. You also get a higher average energy, X-ray energy, which means a decrease in the dose of the patient. Does everyone understand why that's a decrease to the patient? So, if you remember, the lower energy X-rays are more likely to be absorbed. So, they don't get through the patient, so they don't hit the X-ray receptor, so they don't contribute anything to the image, but they contribute all their energy to the patient dose. So by increasing the average X-ray energy, you're going to decrease the dose to the patient. So the main factors affecting image quality, you've got your MAS, milliamp seconds. So the amps is basically the number of electrons, and seconds are seconds. Kilovolts peak is basically the speed at which the electrons are traveling. Manipulate these two factors. So when we think MAS, we think it's density. So it's directly proportional to density. And these arrows are weirdly in the wrong place. 2 times the exposure time, we're going to increase the density. 2 times the MAS, double the density. Half the MAS, half the density. So it's a linear relationship, directly proportional. So the controlling factor for film density is MAS. So KVP is the main controlling factor for contrast, for K for contrast, but it also can cause a change in density, because obviously you're changing the speed of the electrons, so more are going to get through or less are going to get through the patient. So while this isn't the best way to change film density, it can change film density. So increasing the KVP by 20%, you're going to double the film density. Decreasing it by 16%, you're going to halve the film density. So this is the 20-16% rule. Fairly straightforward. So if you need to change the contrast of the film at all, you want to increase the contrast, you're going to decrease the KVP. If you're going to decrease the contrast, you're going to increase the KVP. So if you need to decrease the contrast, you're going to increase the KVP by say 20%. You then realise that you need to maintain the same density. So what you're going to do is you're going to have to halve the MAS to maintain that same density. And then vice versa, if you need to increase the contrast or get a more black and white image, you're going to decrease the KVP by about 16%. So then you're going to have to double the MAS to be able to keep that same level of density. So KVP, the shortest wavelength or the highest energy X-rays are determined by the KVP. So the contrast and KVP are inversely related, like I just said. So you increase the KVP, it's going to decrease the contrast. If you decrease the KVP, you're going to increase the contrast. So the controlling factor for contrast is KVP. K for contrast. Source to image distance. So this is the distance between the X-ray tube and the image film receptor. So all radiation obeys the inverse square law. So it's because it's dispersed in all directions equally, it starts to get less and less intense the further away from the source you get.
So if you increase the source to image distance, you're going to decrease the film density. Obviously, if you take the source or the image away from the other, you're going to cause less X-rays to reach the film receptor, so that decreases the density. It obeys the inverse square law, so doubling the source to image distance is going to decrease the film density by a quarter, whereas halving it is going to increase the film density by 4 times. So line focus principle. This one I might go a bit slower through because it takes quite a bit to understand them. So using the target, which is the rotating anode, you can angle that. The effective area of the target will be decreased. So because the X-ray beam is coming in like this, if you change the angle of the target, you can either have a bigger spot that it hits on the target or a smaller spot that it hits on the target, effectively. The effective area or effective focus spot size is the area projected onto the patient. And when the target angle decreases, the focal spot decreases. So that's basically the main point you need out of this. When you decrease the target angle, you're going to decrease the focal spot size, the effective focal spot size. So here we go. As the electron beam hits the target, you get the actual focal spot size, which is the actual size that hits on the target, and then you get the effective focal spot size, which is basically the size of the X-ray beam that hits the patient. If that makes sense. By changing this target angle, you can change the actual focal spot size, and you can't change the actual focal spot size. The actual focal spot size is the beam of electrons. It's always the same, no matter how you change the target. The effective focal spot size will change depending on how this is angled. So the smaller the anode angle, the smaller the effective focal spot size. The larger the angle, the larger the effective focal spot size. So if you can imagine that the target angle was completely vertical, or you had 0, the smallest angle, there would be no effective focal spot size because you wouldn't be able to see where the electrons are hitting the target. Does that make sense? Whereas if you change this angle to 45 degrees, you're going to be able to see a lot more of the face of the target. Hopefully that makes it a bit easy to understand. It's a confusing concept. But yeah, the smaller the angle, the smaller the focal spot. Just remember that and it'll help you with any of the questions that are in the file. So moving on from this, the anode field effect. The anode field cuts off one side of the X-ray beam. So remember, when the electrons hit the target, they produce X-rays in all directions. So some of the X-rays are going to try and go this way, but they're going to get cut off by this part, and that causes the anode field effect. So this causes a decreased beam intensity at the anode end. This can be used to your advantage. So here you go. The heel of the anode is just cutting off some of the X-rays. So on the cathode side, you're going to have more intense X-ray. On the anode side, you're going to have less intense. So what we do with this is we can place the anode side towards the thinner side of the patient. So rectification, hopefully you remember all what rectification is. The process of converting AC to DC. So all of the power that comes out of the wall and around the world usually is AC. Generating X-rays, you don't want that back and forth voltage potential, you want just straight DC. So this is carried out by a rectifier, and that ensures electrons only flow from the cathode to the anode. AC will just blow up the tube, so it won't work at all. So different types of X-ray production. Oh, sorry, this is characteristic radiation production. So I think we're moving this way. So we have a projectile electron coming in here. It's knocking off that inner shell electron, so the K shell electron. The projectile electron then flies away, and the ionized K shell electron flies away. What we then get is one of the outer shell electrons dropping down to fill that empty shell, because this is an unstable.
by dropping down, it releases energy, and that energy is released in the form of an X-ray. So this can happen from anywhere, any of the other shells, and releases those characteristic energy X-rays that are the same if you're using the same atom. So for tungsten, which we use, you're always going to get the same energy X-rays because of the binding energy of the electrons. Basically the same thing. Bremsstrahlung radiation, so this is the German word for slowed down radiation or braking radiation. So this is produced when projectile electrons are slowed down due to an electrostatic force of attraction with the target atom nucleus. So as you see here, the projectile electrons flying close to the nucleus. It's then attracted to the protons in the nucleus, which causes it to change its direction. This releases some energy in the form of a very low energy Bremsstrahlung X-ray. If you have a greater deflection, there's a greater change in energy, so more energy is